Good morning, everyone. Good morning. Good morning, everyone. I'm actually very happy to see everybody in the room. It's the last day of CPDP. I think not just the program, but also the parties were amazing. Lots of hallway conversations. My name is Rob van Eijk. I'm the Managing Director of the Future of Privacy Forum in Europe. Yeah, please feel free to, there's some seats still left here in the front. Managing Director of the Future of Privacy Forum in Europe. At FPF, we provide a forum for a diverse range of views and voices to discuss the complexity in a data-driven world. And we help privacy leaders learn from their peers and from experts. And today we actually have three data science experts amongst us to discuss and learn about pseudonymization and anonymization technologies. We will learn from these practitioners who will try to explain the intricacies without any mathematical formulas. So it's intended to be a transposition towards a non-technical audience. The agenda, how we will serve the content to you, will be that I do a short introduction, which sees to zooming in on the infographic that's on your seat. Then we give the floor to Sophie Stalla-Bourdillon, and Professor Bourdillon is a senior privacy counsel and legal engineer at Immuta, and professor in IT and law and data governance at the University of Southampton in the UK. Then we have Naoise Holohan, who is a research scientist in the Dublin lab of IBM Research, a leading research on differential privacy with AI security and the privacy team. And his interests center around developing user-friendly tools for data protection and exploring new use cases for the technology. And the closing presentation will be by Lucy Mosquera from Replica Analytics on synthetic data. And Lucy is the director of data science at Replica Analytics, recently acquired by Eijk. And at Replica Analytics, she is responsible for leading the team that develops cutting-edge methods and data synthesis, and the assessment of synthetic in terms of privacy and utility, as well as leading customer projects. Having previously worked in clinical trial data management, she has a passion for improving the efficiency of health research and making the most of existing data sources. Well, with that, we'll share the slides later with you. We obviously are intricately familiar with the identifiability challenge that is in the GDPR. It's identifiability to a natural person. And the Article 29 has written in its opinion on 2014 extensively on the different criteria, how to go about the assessment whether data is pseudonymous or maybe anonymous. And with that, obviously, the recital 26 is in the background of the discussion today, where account should be taken of all the means reasonably likely to be used, and singling out specifically in the context of data science and machine learning is an important aspect. And we have seen, for instance, with location data sets that behavioral patterns can still exist, and maybe the risk is very low, but the impact on the personal privacy could be very high when this data is re-identified by an attacker. But it's also interesting to understand that if you are like a staffer at the DPA, and I used to work on enforcement cases at the Dutch DPA, the staffers have to make a case and prove that identifiability to a natural person is actually possible. So, and there's a threshold with all means likely to be used, and this includes the cost for the technology and the staff to be used, but also the state of technology. And obviously the state of technology of 10 years ago is very different than the state of technology now. And this makes it very interesting to see, okay, but how is that state of technology developing since we have seen the EDPB guidance from almost 10 years ago. So the EDPB guidance is most likely to be released in an update in public consultation later this year. And the three, just to sketch out the background a little bit before handing the floor to Sophie. It's the singling out, the linkability, and the inference elements that are actually when in the discussion on identifiability were on top of mind of the data protection authorities in their guidance. So if we zoom in on like direct identifiers and indirect identifiers, but also on technical and organizational measures to prevent unlawful processing, I think it's fair to not just draw the line and say, okay, on the right side it's anonymous data and on the left it's personal data. It's more about what is like a wise way to go about protecting the personal data. And that's why we introduced a term called protected de-identified. It's not an official GDPR term, but it's to show that data has been processed and is being protected, safeguarded with technical and organizational measures such that it most likely cannot be used for other purposes than the initial purpose that it was designed to use for. So I leave the infographic for you to read on your way home. And I think it's fair to shift to the first presenter. And with that, I warmly welcome Sophie to take the stage here. Professor.
This way. Okay. I have a big computer. Need to play.
Good? Yes.
Okay, this is the title. So, hello everybody. Thank you so much for being here. I'm Sophie. As Rob mentioned, I have one leg at the university. I've got a legal background, but I'm also working in industry with Immuta, which is a data governance solution. An access control platform that allows to create the audit trail and govern data in the analytics environment. And we've got some de-identification solutions into the product. I was supposed to be joined by my research scientist. Unfortunately, he has tested positive just before the conference, so I'm going to be alone on the stage. So you will have to be nice with me. I don't have the mathematical background to explain some of these things, but I'll try to be as clear as possible. And actually, just for more background, we are working as a team with Alfred to try to develop an approach to explain what these pets are actually achieving. The ultimate goal is to be able to inform those who don't have the technical background. So even if my speech is not going to be perfect, I think this is a useful thing to do. Start with a warning. It's going to be a little bit painful. I'm going to try to dive into some of the details to show you the complexity of the space, but I'll try to do my best to be clear. This is the only way to warmly welcome the pets, I would say. If you want to see them as cute animals, then you need to go into the details here, I think. We had divided the session into 4 sections. A short introduction to set the scene correctly and show that there is not one way of doing things. Then a deep dive into homomorphic encryption. Then going back to the people, understanding who is who and what they're actually doing is actually essential to be able then to do the legal analysis on top of the technical implementation of the PET. So that's why it's important to identify the parties, and it's super also important if you want to do the risk assessment afterwards. You need to go back to the parties to be able to do that. And then some illustrations. I'm going to add some use cases to show you how this can be actually used. So let's start with the introduction. PETs, a data protection technique that makes it possible to embed legal or compliance requirements within a data processing pipeline. Yeah, very generic definition. In that bucket, you can include many things. One thing very important to bear in mind is that not all PETs are actually equal. As a third stage, it's very important to specify your data protection goal to assess PET achievements. Where are these goals? The starting point will be, well, within the framework itself. Article 5 has the goals. Some are explicit, some are more implicit. The last one, intervenability, is more implicit than explicit, but it's there particularly if you combine 5 with 25, and then other provisions in relation to their subject rights. But you will see that confidentiality is one out of many, okay? For the same data protection goals, PETs don't offer the same formal mathematical guarantee. This is how you distinguish between them. And actually related to that, PETs may or may not assume a trusted processor. And when I say processor here, I don't mean processor in the legal sense. I'm speaking about the party that's actually doing something with the data, okay? Assuming we have one, because not all PETs assume a trusted data processor. So as a high-level distinction, you've got two buckets. You've got the soft PETs on one side and the hard PETs on the other side. The soft PETs often assume a trusted data processor, and therefore assurances are also derived from organizational controls, such as legal obligation, in order to tame your processor, monitoring and auditing to make sure he's behaving according to standards. And then on the other side, we've got the hard PETs, which are robust to misbehaving, malicious, and negligent data processors. And their assurances are derived from mathematical guarantees, mathematics. And often no second or third party protocol participant can violate their subject confidentiality. Okay? So here's the one list that we've generated. You will see that on the software side, you find federated learning, synthetic data, access control, encryption. Encryption is actually on both sides. Why? Because it depends on how this is being used. If it's being used for internal purposes only, you are still managing the key, then you need your organizational measures to be able to control access to the key. So this is why it's there, and this is why this is being presented actually in GDPR as a security measure. But the part that is often being missed is that if you look at the external use of encryption towards a third party, then there is a mathematical guarantee here. So arguing all the time that encryption is only a security measure might not be the best way to present the technology here, I would argue. Secure multi-party computation is hard PET, partially homomorphic encryption is hard PET, fully homomorphic encryption is also hard PET, as well as differential privacy, which will be presented after me. This being said, these hard and soft PETs are not so disjoint, and I'm going to explain very quickly why. In fact, I mean, the claim that we like to make is that they should be used in combination, these PETs, because each PET is going to address a specific problem and is going to shield a specific actor. Yeah. So I'm going to explain that in the context of fully homomorphic encryption, but to start with, I can start with an example borrowed from the federated learning space, which is a soft PET, but which can be hardened. So let's take autocomplete, for example, word completion, if you prefer, that you have on your smartphone. You've got a global model that captures trends in slang or phrasing. Your phone updates the model personalized to you. The global model is subsequently updated by incorporating everyone's local model. And then updating the global model from local modem seems like a good idea at first glance, because only aggregate data is exchanged. Yeah, so lawyers feel safe when they see aggregates. They love aggregates. They love statistics. They think it's safe. No problem. I can do whatever I want with that. Yeah. Well, it's not exactly true, actually. Federated learning could be represented, therefore, in this way. You've got a service provider that sends model updates to personal edge devices. Edge devices update their local models with local data. And then the service provider updates the global model from local models. Yeah? But wait, how do we know that the push to the provider does not reveal anything too private? Like my high frequency words could be telling, for example. Or that the provider does not push anything too private to the other devices. Like phrase prediction might allow others to autocomplete with snippets of my private messages. But the true answer is that we don't. Aggregates can be rich, and aggregates can memorize or signal in completely unexpected ways. Even simple ones, like a single average, could signal the participation of an outlying individual. But that's not the end of the story, because we can harden the pet if we want. And we could do that through another technique, which we then combined with the first pet through, for example, local differential privacy. Okay, that was just my introduction to set the scene. So now let's do a deep dive into homomorphic encryption. Homomorphic encryption allows computing of encrypted results directly from encrypted inputs without, that's a big word, any intermediate decryption or even knowledge of the decryption key. You've got two types of homomorphic encryption. Partially homomorphic encryption, which supports only one kind of operation, addition or multiplication, and on the other side, fully homomorphic encryption, which supports evaluation of arbitrarily complex computation. That's what we will get in the future. We don't have that. Well, we have that, but I'm going to show you the good things about it and also the bad things about that. This is based, you've got several crypto systems available. The first one was textbook RSA. The properties of that system is the following. Multiplying ciphertext in encrypted inputs gives a ciphertext of the multiplication, but there is also another one, for example, the Pallier one, for which multiplying ciphertext gives a ciphertext of the sum, but I'm not going to go into details here because my knowledge stops there. The good thing about partially homomorphic encryption is that it's typically much faster than fully homomorphic encryption. And the bad, obviously, is that the applications are actually limited by having to stick to one kind of operation. Okay? The new kid on the block is therefore fully homomorphic encryption. It has been sought for since RSA, the crypto system that I introduced earlier. Since therefore 78. It's only until 2009 that we have a proper way to do that. Until 2009, we had what data scientists were calling somewhat homomorphic encryption. So it's a relatively recent solution. And this is made of 4 operations. The first one is the creation of the key, the generation of the key, then encryption. You encrypt your inputs, then you decrypt, and you evaluate homomorphically upon the encrypted data. So you apply code there, and there is no need to decrypt for that purpose. The good thing is that it allows general computation over encrypted data. And for the lawyers, it should open up the possibility of processing in third countries, because it's offering you a guarantee against the people actually processing the data. This is not to say that it's going to solve every problem and every legal problem. I'll try to explain that. The bad thing is it's relatively slow, often 1,000 to 1 million times slower than operating on unencrypted data. So adoption is slow, likely due to speed and complexity. A few pictures to illustrate the different stages. Usually, you can have 3 types of keys: the private key that is used to decrypt, the public key that is used to encrypt and can be shared, and also the evaluation key that is used for the evaluation stage, for the computation stage. In many instances, both the encryption key and the evaluation key are the same. They are both public keys. These can be shared without jeopardizing the encrypted data. So I've got my user, she's called Alice. She's very nice, she has some data, she's going to encrypt that. She keeps the private key. And then this data could be eventually decrypted at a later stage by an algorithm to produce unencrypted results. But obviously, not every key is going to be able to decrypt. If you use the public key, you cannot decrypt. And then I've got the evaluation stage. I've got the encrypted input, the evaluation key, and the code, and I can run the code without having to decrypt. That's the beauty of it. Now, a few words about the parties. So I've got three main parties. My Alice, my data holder. So here I'm not speaking GDPR language. Bob, processor, not in the legal sense. And Carol is Alice's collaborator. If I put that into the GDPR world, this is what I could get. So there are different types of options. It depends on the scenario that I'm working on. Alice could be a data subject or a controller. Bob could be a processor, a control, nothing. So it depends on which approach you take towards anonymization. And then Carol, a controller or a joint controller, or control in common if you use the terminology that the ICO is actually using to distinguish between situations here. The first party is Alice. She's the data holder. She'd like to collaborate with others. The second party is Carol. Carol collaborates frequently with Alice. And the third party is Bob. He's a processor who may be nosy. So let's have a look at a few use cases so that you understand when that can be actually used. Electronic voting. Electronic elections are a frequent debate. The cryptographic feasibility of electronic voting is only a small factor, okay, in a broader and more nuanced picture of electronic elections. I'm not advocating for electronic voting necessarily here with that slide. It's only to discuss a potential implementation through the technology here, which could go beyond governmental elections, actually. So partially homomorphic encryption can be used for electronic voting. This is not to say that every implementation is going to work properly. There are flawed examples, and one of them is on the screen here. You can get it wrong even if you use the technology. Yeah? In particular, if you do not take care of auditability, secrecy, you give every power to your administrator who can decrypt the vote. That's not really good. And you're also vulnerable to repeat voting. This being said, it's possible to construct an end-to-end verifiable protocol with the following properties. Validity. Only valid votes of eligible voters are counted. Individual verifiability. Each eligible voter with a valid ballot can verify inclusion of their vote. And auditability. Protocol conformance is checkable here. You might need to add an additional layer of protection through the raw knowledge proof, for example. That was one use case with partially homomorphic encryption. Personalized medicine. So here, that's the use case. Bob is a personalized medicine provider and has an excellent algorithm for predicting drugs' efficacy as a function of an individual's genetic profile. Okay? And he resides in a third country and would like to keep his algorithm confidential without sharing the algorithm with someone else. And then we have Alice, who would like a recommendation and to keep her medical information private. She wants to make sure that never on earth Bob is going to have to be able to actually access the data. She has the keys, she has the data, he has the code. Alice, therefore, in the GDPR terminology, would be their subject. Bob, we can discuss. She encrypts, she sends that to Bob, who cannot decrypt. He runs the code. He produces an encrypted result that is then shipped back to Alice. And Alice is only is the one decrypting the message and is the only one being able to actually read the results. That was one option. The second use case I wanted to introduce is learning a model from a sensitive data. So Carol is, let's say, is a medical infrastructure strategist who wants to model and evaluate clinic demand through simulated patient encounters. And to this end, she's developing a generative model that outputs random encounters from real patient data. And Bob, again, is my third-party provider of cloud computing infrastructure for machine learning, and he has lots of computing power. So assuming Carol has a legal basis to further process clinical patient data, she wishes to contract with Bob to train her model. And so that's the diagram that we would get. Option 1 would be to use fully homomorphic encryption. Carol has the data, she's the one encrypting the data, so she has access to actually plain text data. She encrypts the data, she ships that to Bob, who is running the code and the computation, and but Bob cannot decrypt the data, cannot see the results in an encrypted way, and this is shipped back to Carol. So here again, if you want to speak the GDPR language, this is probably what you would say, and we can discuss again what Bob is actually. There is a variation of that implementation if you use a multi-key implementation, what is being called multi-key fully homomorphic encryption. In this case, every data subject, every Alice keeps the key, the private key. Okay? So by doing that, you are releasing less information, obviously, to Carol. And so you are shielding more parties by doing that. But Carol is going to see some of the results, and depending upon the question that is being asked, it might be, the inference might be personal data as well. So this is why I still have Carol as a controller. So this is essentially how that would work. The code is being shared with Bob, who is going to run the computation on the encrypted data. Alice's keep the key. This is shipped back to Carol, the results, yeah? And at that point, the Alices agree to share the private key so that Carol can decrypt the results without seeing the input data. Okay, so that's how it actually ends. So I've added a table at the end here, so trying to try to do the risk assessment here and to show you how you should be doing the risk assessment by stakeholder. Yeah, I've got my processor, my collaborator, and potentially, if that's relevant, also my model user. The way the information is being protected is going to depend upon the role of that user. So it's rather a complex assessment, but if you want to do it properly, that's how you should be doing it, and you are going to see that in that context, the model is not protected. Okay, but can't the model leak? But in some cases it could, for example. So you could go beyond that, and this is why I've said it's important to think about combination of pets. This is where I introduce you to Dave. Dave is a data user, is a model user. He has legitimate access to the model, and he likes to reverse engineer things. So he should be also considered an attacker if you want to do things properly. One way to protect the model is, as I mentioned earlier, to use another pet, to use differential privacy, for example. I'm not going to go into the details here, obviously, because this is going to be explained after me, but essentially that will allow Bob not to be able to properly guess whether Alice had been included within the data set in the first place. So Alice gets some deniability here. And then you have some further variations. Where can we add this extra protection? Again, the decision to add noise can be made at different points of the data flow, and it's going to depend upon your risk assessment. So here, this is being made by Carol. You see, she's receiving actually unprotected data, but she's going then to encrypt and then instruct Bob to inject noise as well. So these generate a certain risk assessment profile that might be different from other risk assessment profiles. In that picture, in that data flow, Carol knows all patient data, Bob knows no patient data, and my model user, Dave, because I've got DP applied on the data. At worst, so here obviously there are some complexities that are going to be explained. He knows low individual information. But obviously, protecting the model has also some utility consequences. Yeah, so that also needs to be taken into account. Another way to inject noise would be to use local differential privacy. This is also going to be explained, and that can be done at a different point in stage, triggered directly actually by the data subject, assuming we help them understand how this should be done, obviously. And so my risk profile is slightly then different than from what I had earlier, because what Carol is getting now is randomized identified patient data. Okay, so the sensitive attributes are getting a little bit protected in that case, a little bit are getting protected. This is still personal data though. My last use case is what we call secrets in common. So I've got many Carols, a consortium of Carols, of specialized clinics who'd like to determine patients in common without exchanging patient lists. And there are multiple paths to victory here. They differ only on their risks. Again, it's about risk assessment. And you need to do that by, as I said, by stakeholder and party. So Bob, in that case, you use a trusted third party. That's the first option. Bob acts as a trusted third party, is a processor, therefore. Option 2, multi-key fully homomorphic encryption. Bob acts as a service provider and blindly computes the intersection by way of multi-key FHE. Here we can argue. And then option 3, secure multi-party computation. We got rid of Bob by using SMC. But that does not mean that we are necessarily reaching the anonymization standard here, again, because we need to understand what is the type of query that can be made over the data. If my party is able to infer new attributes that are relevant to individuals, then this is still personal data. This is why it was a little bit confusing that we had that in the recommendations from EPD on EDPB on international transfers. So it's not that SMC is not necessarily the best solution ever that is going to put you outside of the framework. Again, if you want to do it properly, then you need to, as I said earlier, do the risk assessment by actor, by threat, okay? Inference and sabotage are not necessarily the same thing. And obviously, understand the practical barriers to implementing your bet. Conclusion. I've done it. That's already a success. I hope you've understood something, yeah? Don't ask too many questions, though. I don't know whether I will be able to answer, but I'll try. The main message I'd like to convey here, though, is that it's hard, if not misleading, to try to present the pets on a spectrum. As you've seen, when you do your risk assessment, you need to look at each actor or stakeholder and understand to what extent is being shielded from the data or the query results. Okay? And to say a few more words as a concluding remark, homomorphic encryption is a unique and promising privacy-enhancing technology, enabling blind computation over sensitive data. Partially homomorphic encryption is there, can be used today, fairly quick and very usable, but there are some limitations, as we said. You need to pick an operation. The importance of fully homomorphic encryption cannot be understated. However, obviously, it remains hampered by complexity of deployment and often extremely long compute times for even small-sized workloads. Here, again, you need to understand whether you want to work in real time or not. If you need to work in real time, then that's a bit more difficult. But it does enable computation by untrusted third parties and open up access to service providers located in third countries. And that's the reason why we had this as a safeguard within the recommendation. Although I'm not entirely sure that EDPB is getting right the distinction between encryption and anonymization, unfortunately. More generally, pets do not compete so much, okay? They should act as complements if you want to do things well. And often, therefore, many pets must be deployed in thoughtful combinations in order to mitigate all data processing risks. And with this, I highlight that, and I close.
Thank you, Sophie. This was really challenging and really, really impressive. Thank you very much. We are going to do one or two questions, but maybe it's more like a discussion because, well, Alfred's not here, but it's going to be very enlightening to see maybe the first question, whether there are any clarifications. So, Sachiko, first. Yes. I'll give you the microphone to make sure that we record.
Hi, Sachiko from Axiom. So to begin with, I'm going to embarrass myself. I didn't get the meaning of what is the difference between a homomorphic encryption and a normal encryption. I get it that you use keys. I get it that you used pets, but what makes it homomorphic and what doesn't? The other questions that I had was, secure multi-party computation. I get it that you got rid of that guy, right? But how does it work? Can you actually explain it to a layman's term, if you would may?
So homomorphic encryption is a mathematical concept. Essentially, that means that you can, well, if I oversimplify, because that's the, I guess, only way I could explain that. So you can run the computation over the encrypted data without having to read the encrypted data. Okay? So you preserve the properties of the encryption over the data homomorphically to run the computation over the data. So he's blind. When he runs the computation, he's blind, and he doesn't even see the results of the computation. The results of the computation, the correct results, are being shipped back to the holder of the key, who will then see the results to the computation. So those who actually see the input data and the results of the computation are the ones who should be considered potentially controllers or even processors, because this data can be personal. But to the guy who is running the computation over the encrypted data, he doesn't see anything.
Yeah, if we make it very visual, if you put the data into an envelope, you do the processing just on the envelopes without knowing what's inside of the envelope. That's the homomorphic part of it. Yes. David.
So I have questions regarding the limits. So you said it takes a lot of time to do the computation. And is there in the foreseeable future any solution to that? And closely connected with that question, what are the costs of the technology? So what are the implementation costs? And the other question would be looking at the learning from sensitive data example. If you run an algorithm on encrypted data, how do you protect from reverse engineering this algorithm? So you need a different pet for that, right?
For which algorithm?
So you have the learning from sensitive data model. And as I understand it, you run a learning algorithm on the encrypted data. And there are methods for re-engineering these algorithms.
So the output that is being produced, so the trained model, so you can have some code that is going to be used then to train the model with some data. The code that is being produced before the training.
Yes.
Obviously, this you can, if you have access to that, then you can sabotage the code if you want. But the results, which is the trained model, this can remain encrypted and will be decrypted by the model user.
Yeah, and this user could run a reverse engineering attack, as I understand it, maybe depending on the algorithm which is run, right?
So yes, that's why I spoke about differential privacy. The model user is potentially, if he's conceived to be an attacker, then you need to protect the model itself as well.
Okay, thank you
Because
for
you are
that
concerned about the behavior of the
yeah.
model user.
Okay, thank you for that clarification. And can you address the point with the cost?
I'm not the best person to, I'm not entirely sure here. The only thing that I would say is that I've spent the last 2 days with one of the best crypto guy here. He's not. I don't see him in the room, unfortunately. He's saying that should be used more because some technology is available. If you want to do things in real time, it's a little bit more difficult. But from his perspective, there are already things that can be done today that are not too expensive. Now, if you want figures and numbers, I'm not going to be able to do that, but I could certainly go back to you through emails involving Alfred, who must be sleeping.
Let me add, this was the last question before we go to Nisha. If you're a DPO or a CPO, I think it's important in the project phase to interact with the data science teams as early on as possible. I think there are so many complexities, and the identification of risks attached to these safeguards, when they are so mathematical and complex in a network of different actors. I think this, what we really need to take home today is that the identification of risks is complex. If you don't have the technical background, it's very difficult to understand these risks. But the two worlds need to talk to each other as early on in the project, I think, as possible, maybe already in the project initiation document. So, well, thank you very much, Sophie. I really enjoyed the presentation and the interaction. I want to give the floor to Nisha, and I close with a round of applause, please.
Right, hello. See, we're working great. First of all, thanks to Rob and Sebastião for the invitation to speak here today. It's great to see everybody back in a hall together. It's been a very long time for me anyway. So my name is Naoise Holohan. I'm a research scientist in the Dublin lab of IBM Research. And I'm talking to you about differential privacy today. So it's nice of Sophie to give me a plug and give differential privacy a plug. So hopefully you're all convinced of its use already. Before I get into DP per se, I just want to give a quick outline of IBM Research because people are sometimes confused as to our existence. So we're in existence for 77 years and we work, well, we're within IBM Corporation, but we're dedicated to science, and you can see from the list of accolades and awards that our researchers and engineers have won over the years that that's a testament to our work. We're spread all across the world, and with a particular concentration in Europe, which is obviously where we are in Dublin. There's 3,000 researchers across scientists and engineers in IBM Research, working across hundreds of disciplines with worldwide collaboration within IBM Research itself and within with our partner universities around the world as well. Of particular interest for this talk is our work on computer science, mathematical sciences, and on security and cryptography. So before I start on differential privacy, which is I guess the future of anonymization, a quick word about what I term traditional anonymization. So these are tools that have been in existence for 60 plus years that we still use to this day. And these are a list of some of the important ones that we use. So we have suppression, which is basically the removal of records from a data set. That can be the obvious things like removing people's names, social security numbers, addresses, and can also include removing individual components of data. Generalization involves the change of data to more general terms. So, for example, changing a single number to a range, changing a city to a country, and more umbrella terms like that. With masking, we replace values with fictionalized ones, sometimes randomized. Tokenization then is where you replace a unique value with a token that is sometimes reversible. I guess in this particular context, that's more associated with pseudonymization, but we, in our work anyway, we kind of pile them all in together. And finally then, k-anonymity is a more recent protocol that we use to combine all these tools together to produce k-anonymous data sets. So there's an example here on the right where we have a data set of age, sex, and disease. In this particular data set, the disease is the important characteristic that we want to preserve, so we don't apply any anonymization to that. But then we use some generalization on the age to ensure that every combination of age and sex in the output data set appears at least twice, and this gives us a 2 anonymous data set. So you can see here, if you know that there is or I guess one issue with k-anonymity is that is represented here, that if you know that there's a 27-year-old female in the data set, from the anonymous data set you automatically know that that person has HIV. So in that particular context, the anonymization hasn't worked to protect the privacy of that individual. So this brings me to, I guess, the lay of the land. So as I said, these tools are about 60 plus years old, and the landscape in which they reside have changed a lot in those years. So we now have the internet, and the risk of being able to link these so-called anonymous data sets with external data on the internet to expose sensitivities in the anonymous data are now huge. There are many examples of this having happened in the wild, and I've got 3 of them listed here just for your interest. So in the Netflix case, back in 2006, they published a data set of anonymized movie ratings, and researchers were able to link it with the publicly available IMDb, which is the Internet Movie Database, which is a public forum. So anything you post on IMDb, typically your username is attached to it, and it's available, and it's published publicly. And the researchers were able to link the 2 data sets together and identify individuals in the Netflix data set and identify ratings that they'd made in private, assuming that they would be kept private by Netflix. And you can imagine that might expose a lot of sensitive information about yourself in that context. In the AOL case, they published a data set of anonymized internet search logs, and the New York Times were able to dig into the data and single out a particular individual. And I think they went to her house and they basically gave her a printout of all the internet searches that she had done. In this context, it wasn't actually linking to an external data set, but the data itself was rich enough to be able to single her out. I think the example I always give is we all search our own name probably more frequently than anybody else, so that's an immediate pointer to your internet search logs. And then the New York City Taxi and Limousine Commission published a data set of anonymized taxi trip records in New York City, and a blogger was actually able to link it to photographs of celebrities getting into taxis in Manhattan. I think that's Bradley Cooper in that photo, and they were able to actually single out the particular record that trip was associated with, and find out where he was traveling to and from and how much he had tipped the driver. So that's more of a fun example of things that can go wrong. Now, in all those examples, you could tell me, oh, but if you did X, Y, or Z, you would have protected against that particular attack. But that in itself points to the ad hoc nature of the traditional anonymization tools and how we use them. The typical scenario is a user has to make a decision on the type of anonymization that's applied, and that decision is typically based on assumptions that are made on an attacker. So you might assume that an attacker might have particular knowledge of individuals in the data set, and you can implement an anonymization protocol to prevent against that, but you don't have any control over an attacker that might have more knowledge, for example, or knowledge that you don't know an attacker has. These are all examples of attacks made on data sets that were anonymized and then published in the wild, but similar risks exist when you're giving access to sensitive data sets, either through a query engine or simply in a controlled environment. And that extends to, as Sophie was explaining earlier, to machine learning, where you're trying to learn a model on a sensitive data set to achieve a particular task. And in our field, we have the very important database reconstruction theorem, which tells us that answering enough queries, enough accurate queries on a data set can allow you to reconstruct the entire data set. And that in itself means that having control over the type of queries we ask isn't quite enough, that there's still a risk of re-identification, of inference that we don't want. So that brings us to differential privacy at long last. So based on these failures of traditional anonymization, as I term them, differential privacy was first envisaged in 2006. And the key idea with DP is that we blur queries that are executed on sensitive data. Now that's a very general statement. And queries especially, I want you to view that as a very general query. So in this context, a query could be, give me the number of people in this data set, right up to train me a deep learning neural net on this to perform a very complex task. And differential privacy is general enough to allow us to anonymize all of those tasks in a common framework. The idea with differential privacy is we use specially curated or specially calibrated random noise in the query process to preserve the privacy of individuals in the data set while still allowing aggregate or population queries to be accurately observed. And I guess the unique selling point of DP is that it's future-proof. And by that I mean there's no data set that can be published tomorrow or in 10 years' time that can undo the anonymization we've applied. And that stands in stark contrast with the tools I presented on the previous two slides, where a particular data set published later on can completely undo the anonymization that's been applied. To give you a very simple example of DP in action, in this case we're going to do a survey of a bunch of people answering a yes-no question, and we're going to gather their answers together, but we want to publish something at the end that is telling us about the survey but still preserving individuals' privacy. So what we're going to do is we're going to randomly flip the answers that people give according to a certain distribution that we know and that anybody who's reading this survey would know as well. And this means that an individual answer that we report is not reliable. So the first participant there, they actually said no, but the randomized answer that we publish is actually a yes. However, after some fancy mathematics at the end, we can still produce a close answer of the total number of yeses that we had in the survey. So there might be a small error, but it's still reliable population statistics at the end. And this is exactly what we want to achieve with DP and with statistics and data analytics generally, is that, I guess with DP particularly, that the individual privacy is preserved, that we have what we call plausible deniability. You can say that, oh, that was the algorithm that said that answer, it wasn't actually my answer. But that the population statistics are still reliable. The trade-off between the individual privacy that we have and the population accuracy, that can be controlled with the parameters that we have at play in DP. So a bit more detail then, what I want you to view differential privacy as a measurement of privacy. So if you have an algorithm that is doing some analytics and we add our random noise to achieve DP, the epsilon number, which is the symbol that we use for differential privacy, is simply a measure of how private it is. It's typically called privacy loss as well, and you'll understand this when I go through the numbers in a second. But there's extraordinary complexity kind of contained within this epsilon, partly because I was saying that we use the same definition for giving a private count in a data set right up to a private deep learning neural network. And that makes it quite difficult to conceptualize what epsilon is and to put a real world understanding on it, I guess. It's a very intricate number. In terms of the range of epsilon values that we have, so again, epsilon is privacy loss. So an epsilon of 0 means 0 privacy loss, which is great, except the implementation of that is that we simply output random noise that's independent of the data set. So for all intents and purposes, an epsilon of 0 is useless. It gives us perfect privacy, but 0 utility, so it's no use. At the other end of the scale, we have an epsilon of infinity, and this gives perfect utility, but 0 privacy, because we've got the maximum possible privacy loss. And the way you would implement that in practice is you simply answer your query without adding any noise whatsoever. In practice, the epsilon values that we tend to use range from 0.1 up to 10 or even 100, depending on the complexity of the task. And a little more technical detail then, I won't go any further than this in terms of technical details, but for people who are interested, the way it's implemented is that if we have two data sets that differ in a single individual's data, so database 1 doesn't have my data, but database 2 does, the definition of DP means that if we answer a DP query on both of those data sets, then the answer should be similar or the same. And if that is the case, then an attacker shouldn't know whether dataset 1 was used to answer the query or dataset 2 was used. And if they can't determine that, then they can't determine if my data was used in the query. And that's where the privacy comes from, that if you don't even know if my data was used in the query, then how can you make any inference on what my data was? And I went through the privacy laws. Yeah, okay. Next thing I want to talk about is trust boundaries. So this is relevant. I think Sophie was talking about local differential privacy, and Lucy's going to be talking about synthetic data. So I'm not sure if these are accurate terms from a GDPR sense, but bear with me anyway, please. So we can add DP at various stages in the life cycle of data. So we have data subjects, who are the individuals about which data concerns, data controllers who collect data from their users, data processors can collect data from one or more data controllers, and then we have data consumers at the end of the line. Adding DP between the data subject and data controller is when we add noise to the data before it even leaves an individual's device. And that's great because not even the data controller sees the original information. Database privacy is where we take a full data set of people's sensitive information and we jumble it or add DP in a certain way to produce a data set that I guess follows the same patterns. And for all intents and purposes, that's a synthetic data set. And the last one then is query privacy, where we have a bunch of sensitive data and we're looking to answer differentially private queries on that. And the usual way of doing that is you ask the query and noise is added to the answer, which is then passed on to the data consumer at the end. Now, the later along this lifeline or life cycle of data that we add DP, the better it is from a utility perspective, because we can kind of laser focus the noise for a particular task. But the greater the liability, because you're passing raw data further along the chain to more individuals or to more entities. From a differential privacy perspective, the state of the art is still query privacy, because we can achieve very good utility with very good privacy as well. Now, unfortunately, all solutions in data privacy and differential privacy are driven by the use case. So there's no silver bullet. We have a lot of tools, and these tools include traditional anonymization. They're still in use and are required. But I guess if you're looking at what kind of use cases would differential privacy be suited for, this checklist might be a good place to start. So DP is particularly useful if there's a large quantity of data to allow hiding in the crowd in an intuitive sense. That has a tolerance to error in the analytics you're running. Because of the noise that we're going to add, there will be a small amount of error. And finally then, that there's an appreciable privacy risk to justify using this kind of gold standard in privacy. There's no numbers on that checklist because, as I said before, we can tweak the parameters to suit a particular use case. But obviously, you wouldn't use differential privacy to give a doctor access to his or her patient's health history because you want to be able to diagnose and treat someone as best you can. But giving a data scientist access to a hospital's patient data set for, I don't know, disease trend analysis, for example, is a great use case because you have a large quantity of data, it's very sensitive data, and in general, disease trend analysis, a small amount of error is more than acceptable. There we go. So to give a quick example of the type of attacks that differential privacy protects against, hopefully these numbers are big enough that you can see. So here we have a sensitive data set of an individual's information, and we're going to try and attack the first entry in the capital gain column, but only using like common statistical queries that we'd have in any kind of a statistical system. So in the first box here, we're going to sum up all of the values in the capital gain of the entire data set. And then in the second query, which is just beside it, we're going to sum up every value except the first one. And if we subtract the two values, then you should get back the original value in the first row, which is exactly what you see here, 2174. However, if we executed these sum queries with differential privacy, the answer we get back bears no resemblance to the original. And this is an example of an attack where if you have a system that implements query vetting, and an example of that is, or in the past, an example, it would have been acceptable to execute a query if it touched enough entries in the data set. But obviously here we're touching every single entry in the data set -1 twice. So that probably would have passed that query vetting system, but is obviously very revealing of that individual's information. So that's called a differencing attack, which differential privacy protects against. And in terms of accuracy on the aggregate, on population statistics, these are some examples here. So we have a histogram of, I think it's another column in the data set. And you can see the blue is a differentially private histogram, which satisfies our privacy constraints. And the orange is a non-private histogram. By non-private, I mean it's been executed without adding any noise. And for all intents and purposes, those two bars are identical. And similarly, then we've executed a non-private mean of that capital gain column I was showing you before, and a differentially private mean, and they match within 0.00005%. And I think it's important to remember as well that data itself is inherently noisy. You can never collect and store perfect data. And differential privacy, again, is, I guess, it's being added to an imperfect system already. So in terms of the work that we're doing in IBM Research, I think Rob mentioned about my interest in developing user-friendly tools. We have a particular interest in machine learning with differential privacy and being able to learn or being able to generate models that you can, for example, export to a client or to an external observer and use without compromising the sensitivity of your data set. So a very simple schematic here is that we have a sensitive data set and we're looking to extract some knowledge or information in a privacy-preserving way and then pass that output on to a third party or a data analyst or a scientist or something like that who will work with that data without your control. An example here is that we're feeding the data into a machine learning or AI algorithm, and we're going to inject differential privacy to protect the input data set. And at IBM then we've developed diffprivlib, which does all this fancy stuff in the middle. It does the machine learning with DP built in. So what we did was, in order to make it as user-friendly as possible and as accessible as possible, was we started with the Python programming language, which is popular for these particular tasks. We used popular packages that people use in this context, and we wanted to make the user experience almost identical to using those systems. with a lot of default parameter settings to make sure that people were familiar with the software before they even knew it existed. And from speaking to users of the software, I think we've achieved those aims by and large. A little snippet of code here. I don't know if anybody here has used scikit-learn before or Python, but basically what we're doing here is we're training a particular machine learning model. And the idea here is that the trained model at the end can be saved and sent on outside of the secure enclave, for example, that your data might reside in. And you'll still have the protections of not being able to reverse engineer back to the original data set because of that future-proof guarantee that DP gives. And here's some examples of the other types of tasks that you can do them with DP. So here we have some data exploration that we're doing to understand what does the data look like, what's in the data, which would be a common task to do before even doing any machine learning tasks. And all of these again can be achieved with the differential privacy guarantees with good accuracy. And then with more what I term classical machine learning, the literature is very rich in the area, where we've a lot of great scientists who've done a lot of work, and we've implemented a lot of those in diff-priv-lib. So, for example, we have logistic regression, linear regression, naive Bayes, and I guess the advantage here is that these classical machine learning algorithms are well understood, and we can take them apart and add our DP guarantee very well. However, because of the way DP works, it's best suited for low-dimensional data sets because it's easier to achieve privacy.
I have a question, because
yes.
It becomes very technical.
Okay.
The epsilon is a very important term
yes.
for our target audience to understand.
Mm-hmm.
Maybe you can help them that if they interact with the data science teams, what questions should they ask them to basically get a good sense on whether the amount of noise that was added is enough to mitigate a risk, because it's a risk-based approach that we're doing here. We want to use the differential privacy as a means, such that the differential private data set mimics or resembles the original data to a large extent, but there's a trade-off, and the epsilon is a way to express it. So what would be like typical day-to-day questions they could ask to understand, and what type of reports should they ask for to understand whether this is enough to protect the data? Okay.
There's a lot to unpack there. So the standard way of doing it at the moment is accuracy based. So for example, someone will look at a graph like this and say, okay, we're happy enough with hitting 95% of the non-private accuracy, and you select your epsilon based on that, which is an imperfect system, and it's not something that I would advocate for, but that's how it's done. There's a lot of work being done on running attacks on these kind of systems, where you produce a differentially private model of a data set, and you try and run an attack to see, okay, how private actually is it? The issue is that with these complex algorithms, we can't hit the epsilon exactly. So we might ask for, give me a model that hits epsilon equals 1, but the actual privacy that's inherent in it is much higher. So the privacy loss is less.
So if the DPO asks, what did you do with the epsilon and why? Yes, so if the DPO asks, what is your epsilon, and can you explain it to me why it is the value it is, that's a good starting point for this discussion, isn't it? Because they will not be able to read this graph.
Yeah.
So there's a disconnect between the mathematics and the epsilon, and so I'm trying to help them to ask the question, can you explain me what the epsilon means, how you did you apply it, and why did you add the level of noise and you think it's protected? Yeah. Would that be a good approach for them? Or should I ask other questions?
I think the science is still evolving on that, unfortunately. I think I said earlier that there's loads of complexity built into epsilon. I think as more use cases of a differential privacy come out and we start getting more ideas of the epsilon values that are being used, that will give us evidence of what is useful. But I guess to give an example, if you're publishing a count or the average salary in an organization, the epsilon is going to be very different to publishing a machine learning algorithm with differential privacy because we can't hit that epsilon exactly with more complex algorithms. So unfortunately, it's still use case driven. In a perfect world, we could use a single epsilon to say this epsilon is good for whatever task, but we're not quite there yet.
But they should query the data scientist about the epsilon, yes?
Yeah. There should be some reason for using a particular epsilon. Yeah. As I said, at the moment, it's use case driven because if we can't get a certain accuracy from the model, then there's probably no point using it. Yeah. And it's a matter of, can you show me an attack that shows that this works? Yeah, but they're very interesting questions, and it's something that as scientists, I don't think we have grappled with, or we haven't challenged properly or answered properly.
So to take home is the lesson learned. If you do the privacy impact assessment, you identify a risk. I mean, you're sharing or disclosing a differential private data set, but you need to understand whether the epsilon was applied and how well, and let you explain in an easy to understand language how that does, and that's an important conversation to have, I think. I think we can ask some more questions to the audience, yes? We have some more.
I literally had one more slide, actually, I think.
So do we do one more slide, and then we have some more clarifying questions, please.
And this is actually kind of tying back into Sophie's talk earlier. So in our team, our next frontier is in the federated learning space. I think, Sophie, you're talking about federated learning being a soft pet and DP being a hard pet, and that's something we're looking at as well. A lot of the work so far has been on cross-device federated learning, which is Google learning off your Android phone. Given the clients that IBM has, IBM is more interested in cross-silo federated learning, where companies have data sets split across different countries, and they're trying to learn a single model across those countries. And the issue is that you still have, although you're not sharing data, the models can still learn sensitive information, and adding DP into that mix is kind of the next frontier for us anyway in our team. So that is me. I'll hand the floor over to you guys.
Yeah, we have 10 minutes for questions,
Please.
so we start in the question in the back, please.
Thank you very much for this presentation. I really enjoyed it, and I think that differential privacy is an important concept that really led to a paradigm shift in how we think about privacy. My question actually coming back to what Rob also highlighted with the tough questions to ask, because even though you said that it's currently useful for query-based systems where it's more like population data, what I've seen in practice is that there are still huge challenges when it comes to time series data, behavioral data, healthcare data, financial transaction, and the like. And I was curious on the one hand in regards to questions to ask, but also what's your assessment on how harmful it is for the concept of differential privacy, what we currently see ongoing in the world when it's used. For example, that people frame it as mathematical privacy guarantee and kind of letting it fall under the table that if you have a huge epsilon, this basically is just a guarantee for poor privacy protection. And what I find even more worrisome, and therefore I would add this to the list of tricky questions to ask for everybody here, is not only the choice of how large the epsilon is, but also where it's applied. For example, we recently saw this Nature paper on the difficulty of achieving differential privacy in practice, where it was about Google Maps location data. And there they had a super nice epsilon of, I think, 0. I forgot the exact number, but it was really low. The problem, though, was that they applied it to the trip level and didn't account for the fact that in the data set, individuals had more than one trip. So if they calculated the real epsilon, because we always want to protect the individual and not only the trips, then the epsilon skyrocketed in regards to, I think, even 4-digit numbers, which is not really good privacy protection. Or we also sometimes see people who want to apply differential privacy on a column base with the, hey, user, switch it on, switch it off, and suddenly you have differential privacy, which is not really how it works. So I think it's important to also look where is the epsilon applied and if it's actually protecting the user and not the individual, so and not the events or the trips. So my question to you, is it really yet already a future-proof technique, or is there more research needed and also more kind of guidance for users to navigate these complex decisions of how to apply it, where to apply the epsilon, and so on and so forth?
Yeah, that's an interesting example that you give. So I think the basic definition of DP is that it should hold if you swap a user in or out. The issue with things like transactional data is that a single user has lots of transactions, and a decision at the implementation stage has to be, okay, what are we actually protecting here? Are we protecting individuals' privacy that that Naoise is in the data set or not? Or are we protecting that Naoise bought a coffee this morning in central Brussels? And that's a decision that has to be, I guess that's a user decision or an admin decision that has to be communicated when the data set is published, because I guess that you need to understand what you're trying to protect and tell people about that. That makes time series data very difficult as well, because again, are you protecting against an individual's presence in the data set, or are you protecting against an individual's present in an individual location? In terms of the epsilon, in terms of the Nature paper that you mentioned, the common workaround for that is that you limit the number of contributions a user can make to a particular query. So I think in subsequent work from Google, they limited it to 4 events per user, and in that way you can control the amount of epsilon that you're spending. So that seems to be the workaround at the moment. I don't know if that answers the question, but yeah.
Thank you very much. Definitely answered, although the last part would raise the question, does this not significantly diminish the utility of the data set?
In terms of limiting it to only 4 entries?
Yeah.
Yeah. So I would assume that the decision of 4 was made based on some calculation on accuracy. And again, that goes back to a lot of implementations being on an accuracy first basis. So they would have played around with different epsilon values and different user contributions and saw what the best result was. Yeah.
Maybe we can pass Marnix the microphone to Emerald. Here, you first and then Emerald.
Yeah. So I had some question that was more like on a practitioner level about the library, the way it's set up, because differential privacy has always had an issue about the composition, and you kind of glided over, but I think I saw it as in some of the code that you had the budget was something that's set up in the library, and I'm more familiar with like Google's Open Differential Privacy Library, which has the budget there, and I'd just like to know how IBM tackled, first explain the composition aspect of differential privacy, and how IBM's differential privacy library works with the budget. The privacy budget.
Yeah, so composition is one of the cornerstones of differential privacy, that if you execute different queries with an epsilon of 1, for example, you execute 5 queries with an epsilon of 1, then the total budget spend, you simply add up the epsilon values, and the privacy loss for those 5 calculations combined is 5. And that's great because you can control the amount of privacy loss in from a data set by just counting up the epsilon values. So the idea is that you'd have a similar privacy loss if you used 1 query of epsilon equals 5 as you would executing 5 queries with epsilon of 1. In our library, we have an accountant that allows you to keep track of these values. So if you're running a script that's doing lots of data analytics and machine learning, that the system counts up the amount of epsilon you're using, and if you exceed a threshold, for example, that it'll shout stop and say no, you can't go anymore. And I think the power in that is that you can actually keep track of how much privacy loss you're giving away. And again, that's another soft question from a science perspective that we still haven't kind of grappled with properly in terms of how do you manage that in the long term. The ideal scenario is that once you exceed an epsilon or you exceed your privacy budget, that the data set is deleted, but in reality that's not realistic, I don't think.
Before handing the mic to Emerald, I want to say that most of you are familiar with cookies and cookie banners. The core idea of when Google starts dropping the cookie by late 2023 is doing the processing in the Google Chrome browser, and the accountant in the browser, that's the Google privacy budget. So it's interesting to take into account that what we learn here from Nisha, although it's by a different library, their same ideas are behind it to protect the user when the data is shared from the browser to the advertising networks. Emerald.
Yeah, thanks so much for this great presentation, and also thank you for making it palatable for, I guess, the maybe slightly less technical folks here. Now, that being said, I got it maybe 80% of the way there. So maybe a question of a slightly different nature, and maybe also alluding to some of what Rob was saying. I'd love to know, and you may not have any, but maybe something that could be communicated afterwards, is how do you make sure that privacy teams actually have the knowledge to be able to have these conversations, right? Because that's something that I think from I'm a head of privacy for a tech company, and I think that's what's really, really hard, because this is the stuff that needs to be discussed, and also where a lot of risk lies if you don't really understand what's going on. So are there any resources that are really like super layman terms for the non-technical folks that you can refer me to, that I can share with my team, things like that? And then maybe also what's the next level after that? Because I know myself, I often feel that I'm scratching the surface and I really need to understand it better. So anything you can recommend for somebody who's maybe not a mathematician or computer scientist?
I don't have anything to hand. Maybe Rob would probably be a better person to ask on that. But I think the differential privacy is still really new. It's, 16 years old. And we're still trying to get trust in the system. The more use case that we have, like the US Census are using it for the 2020 census to publish data. The way I look at it is that we all, when we log into our banking online, we all trust when there's a padlock on the screen that it's encrypted and that we're safe. Maybe we'll get to a point in the future where we see that differential privacy is implemented in a system and that we trust it. But yeah, I don't know, Rob, do you have any?
I think there are two obvious things to share. One is the recording of this event, which could lead to an interesting discussion, and I'm happy to attend such a discussion, also for the FBF membership. The other thing is that one of the aims of the session of today is to also share that with the data protection authorities. I'll be in Tel Aviv next week doing a condensed version of this masterclass. To the DPA staffers who are actually working on the drafting of the guidelines, and trying to help them also come up with practical use cases that they can discuss, and maybe they end up in the final guidance or not. But I think the second important building block is, of course, part of your weekend reading, which is the EDPB guidance. Yes. Any other questions? Yes, please.
Thank you for your talk. I really enjoyed it. Sorry to keep bothering you about the epsilon. I know you underlined that it's very use case specific, but if we generalize the use cases to a couple of types, for example, training an AI model or releasing data publicly or sharing it with a research partner, are there, to your knowledge, guidelines on the choice of epsilon?
No, there's no guidelines. I guess people are reluctant to make any suggestions because it's so use case driven. The reason for, I guess, to give you an insight into why it's so difficult is that DP is a worst case guarantee that you need to protect against the swapping two of the most different or unique people in the world out and still getting the same answer. And in the real world, you'll never get a data set that is that unique, that it's more kind of along the middle, but you still need to add your epsilon to protect against these really unique values and outliers. And that's why in reality you get more privacy than the epsilon that's being reported. And it's more, the more complex the algorithm, then it's more difficult to do. There are examples of people training machine learning and AI and visual recognition algorithms with epsilons up to the hundreds, and still showing that you actually do get privacy out of it, that you can run attacks that show you can't actually learn anything sensitive, and things like natural language processing models that don't memorize things like credit card numbers and don't memorize social security numbers and names with quite high epsilon values. So the empirical evidence is there, but we don't quite have the scientific understanding yet.
Thank you, Nisha.
Thank you.
And now the last part of the three-piece jigsaw puzzle. It's up for Lucy. Come.
Thank you very much, everyone. In particular, I want to thank the two previous presenters, so Sophie and Nisha. I'm going to be building on a lot of the concepts that you guys have already introduced, so thank you for explaining them so thoroughly. Also, thank you, Rob, and the Future of Privacy Forum for putting this session together. It's been fantastic so far. I hope to continue that with my presentation. So I'm Lucy Mosquera. I'm the Director of Data Science at Replica Analytics. And so Replica Analytics is a Canadian startup that works to build synthetic data in the healthcare space. So my examples are going to be largely based in healthcare data, but synthetic data can be generated in any field. I also mentioned that it's a Canadian startup, so if you have any questions about GDPR or what the EMA thinks of synthetic data, I apologize, I will not be the expert in that area, so please be kind. Is that okay? Can you hear me? Yes. Fantastic. So for my talk today, I'm going to be going through a high-level introduction to synthetic data generation, some different strategies, what it means, how you can assess synthetic data once it's been generated from both a data utility and a data privacy perspective, and some of the key strengths and limitations about synthetic data as a privacy-enhancing technology. So, high level, synthetic data generation is the process of fitting a model to a real data set and then sampling from that model to generate new synthetic observations. So I like to make the distinction between synthetic data from simulated data, because with synthetic data, you always have some sort of real data source that you're using to generate your data from. It's not going to be built based off of theoretical models. It's based off of a real data set that has a high privacy risk that you would like to mitigate that risk. And so oftentimes working with synthetic data, kind of the most popular and flashy examples that you'll hear will be synthetic images, such as the faces on this slide. So these are not real people. These are faces that have been generated based off of a model that has been trained on thousands and thousands of faces to learn what a face looks like. Then you can sample from that model to generate new synthetic faces. For us, working in healthcare data, it's not quite so flashy. We work with tabular data, so similar to what you'll see at the bottom of the screen. So data that comes in a table where each row corresponds to a different individual. And working in the healthcare space, privacy risks for these data can be quite large. So synthetic data as a privacy-enhancing technology has a wide variety of use cases. So this is a publication from one of our collaborators in the pharmaceutical industry to discuss some of the opportunities for synthetic data. So synthetic data as a privacy-enhancing technology is a fantastic way of sharing data internally or externally to your organization. So you can share data that you would not otherwise be able to share within your organization, maybe for training or analytic purposes, maybe for evaluating an external vendor or software, being able to do process improvements that you wouldn't necessarily be able to do as an organization using real data due to privacy concerns. Synthetic data can also be really valuable for analytic use cases, where you can share data externally to conduct secondary analyses on data that would be very difficult to get access to otherwise. One of the opportunities that comes with synthetic data that may not come with other privacy-enhancing technologies is that the real data and the synthetic data that you share with users can be completely separated from one another. So as I described at the beginning, synthetic data can be generated by fitting a model to your real data and then sampling from that model to generate new observations. And so those two phases can be completely separated. So you can have your synthetic data generation model trained on real data in a secure environment. Then you can package and send that model to where your users exist in a different environment. Those users can then sample from the model to generate their own synthetic observations without ever having access to the real data. So this is what we coin a simulator exchange, and it can be a very powerful way of working with data synthesis and facilitating data sharing. Oftentimes, data synthesis can be seen as a bit of a black box, where the different algorithms used are kind of confusing. So I'm going to give an overview of a couple different styles for data synthesis algorithms at a very high level. It's all pictorial, there's no equations. So one really easy to understand way of generating synthetic data is through sequential synthesis. So sequential synthesis is where you model the relationships and patterns and trends in your data in a sequential manner, variable to variable. So your second variable in your data set will be modeled based off of your first variable. Your third variable in your data set will be modeled based off of your first and your second variable. Your fourth variable will be modeled based off of the first, second, and third, and so on and so on. So during your synthetic data generation training, you go through and you iteratively train these models to learn the patterns and trends in your data set based off of the previous variables in your data set. Then, during the data generation phase, you iteratively sample and make predictions through those models in sequence. And so, without having a technical machine learning or statistics background, it's relatively easy to see some of the benefits of this approach. Since you have one model that you can pinpoint for every variable in your data set, you can model in a very customizable and dynamic way. So if you have features that are continuous or categorical, maybe you have a survival outcome, such as in a health data set, you can adapt the model used for each variable so that you get the appropriate performance based off of its characteristics. So sequential synthesis can be quite customizable. It's also good because you can parallelize the fitting because you know exactly what you're going to be training at the beginning, so you can have your models trained in parallel, which is computationally beneficial. So sequential synthesis is a really powerful way of synthesizing data for small and medium data sets. Some other synthesis algorithms that are popular that are a little bit more deep learning. Again, no equations, we're just going to discuss this high level. So the first one I'll talk about is on the left-hand side of the screen, which is what you will hear as a variational autoencoder. Basically, it's two neural networks that work together to synthesize data. So your first neural network takes your complex data and learns how to represent it in a smaller and predictable space. So it encodes your data into a smaller space. Your second neural net, which is kind of like the other half of your bow tie, takes this smaller and expected distribution of data and decodes it and expands it back to your original data space. So the variational autoencoder is a way of using two neural networks to generate synthetic data by first encoding it to a predictable space, then decoding it back to your original space, where your synthetic observations are generated by randomly sampling from your predicted lower dimensional space. So oftentimes you make your lower dimensional space just like a normal distribution, and then you can draw new observations from your normal distribution, pass that through the decoder, and get synthetic observations back. So this is a very powerful way of working with synthetic data generation in the machine learning context when you have a lot of observations. Another approach for synthetic data generation in machine learning is using a generative adversarial network, or a GAN. This is a really popular topic right now, so you may have heard that acronym before of GANs, GANs, GANs. So GANs are similar. You've got two neural networks, but this time they're actually going to be working in opposition to each other. So they're adversarial. So your generator's goal is to take random noise and create the best possible synthetic data. Your discriminator has the opposite goal. It wants to be able to take that absolutely fantastic synthetic data and say, no, I'm sorry, it's garbage. I can tell it easily apart from the real data. And so you take these two neural networks and you train them in this adversarial fashion, iteratively and iteratively, making better synthetic data, better discriminating your synthetic data from your real data, and on and on and on until you have fantastic synthetic data. And so this is just kind of a high-level overview of different synthesis technologies, because I want to demystify the process a little bit. But that's not really the focus of the talk today. The focus of the talk today is going through and discussing how to assess synthetic data and what its implications and opportunities are as a privacy-enhancing technology. So, getting started with that. The first thing to think about when assessing synthetic data is the trade-off between data privacy and data utility. So this is a common concern when working with anonymization techniques and trying to mitigate privacy risks. So Naoise had a very good slide about traditional anonymization strategies. And so traditionally when you're anonymizing data, your goal is to take your big black Sharpie and remove variables that have high privacy risks. Maybe you'll also be generalizing, so taking variables that have high privacy risks and binning them or generalizing them to a higher category. And this is effective, this mitigates privacy risks, but it comes at the cost of data utility. So removing highly valuable analytic features makes your data set less useful. So working with traditional anonymization, you have this data privacy, data utility trade-off. And the same thing can be said during data synthesis, but it's from a little bit of a different perspective. So in data synthesis, the concern is how good or how representative your synthetic data is of your real data set. So if you have a data synthesis model that is overfit and it's far too good, you're going to generate synthetic data that is a copy or an exact replica of your real data set. And so that is not going to be very good from a privacy perspective, but you're going to get fantastic utility because you'd get the exact same results working with that data set as you would working with the real data set. On the other hand, you could have a synthetic data generation model that does not do a good job representing your real data set. In that case, you would have a data set that mitigates privacy risks very well, but it would have very low utility for users because you wouldn't be able to get the same results using that synthetic data set as you would if you were using your real data set. So when working with and evaluating synthetic data as a privacy-enhancing technology, it's all about this privacy utility trade-off, similar to working with any other privacy-enhancing technology or PET. So for my talk today, I'm not going to be focusing too much on utility, but I do want to give you the high-level tools to understand and discern different ways of assessing utility with synthetic data. So with synthetic data, utility metrics can often be classified as broad or narrow. So broad utility assessments aim to compare your real data set and your synthetic data set at a high level, looking at the characteristics and structural similarity of the observations. These utility metrics are usually very easy and quick to calculate. They can be quite comprehensive, such as comparing the distribution of each variable in your real data set to the same variable in your synthetic data set. So broad utility metrics are informative, they're valuable, easy to use, very easy to interpret. But unfortunately, broad utility metrics may not be specific enough for the use case of how you'll be using your data. So that's where narrow or workload-aware utility assessments come in. So these data sets are specifically targeting a use case. Like for example, in healthcare data, maybe I know I'm going to be doing a Cox regression to look at the impact of certain drug use on mortality. So for me as the user, since I know how I want to use my synthetic data, my key utility assessment is whether or not I'm going to get the same results on that Cox regression. So these workload-aware or narrow utility metrics are fantastic at really getting the core of how well your synthetic data can be used as a substitute for your real data on specific analyses. So it's really valuable for data users. And if you know what analysis you want to conduct in advance, by all means, conduct a narrow utility assessment. But that's the problem. A lot of the time when you want to be sharing data, you don't actually know exactly what that data will be used for your end users. So that's why broad and narrow utility metrics kind of need to be used in combination, because you're not always going to know exactly how you want to use the data that you'll be sharing. So skipping into privacy now. In Canada, the main way that we assess privacy risks for anonymized data is re-identification risk. So re-identification risk is the chance that you're able to match a record in your anonymized data set to a real person in the world. And the reason that this is the main privacy risk is because it's a fantastic way of summarizing the harms for sharing a data set. So if you're able to match a real person in the world to a record in your data set, you can learn everything about them from that data set. So if you have a driver's license data set, you'd be able to know their licensing status, the location of that they live, whether or not they have any demerit points on their license, and other sensitive information like that. In synthetic data, it's not that straightforward. Because in synthetic data, since you've gone through and used a model to create all the variables or features in your data set, just because you're able to find a synthetic data that looks quite similar to a real individual in the world, it doesn't guarantee that you'll be able to learn anything about the individual from the other features in the data set, such as whether or not they have demerit points on their license. So to assess privacy risks in synthetic data, we need to have a slightly different approach. So considering a synthetic data set, you can kind of classify your different synthetic records based off of their similarity to real records. So in your first case, you may have real individuals that are almost exactly duplicated in your synthetic data. Now, this is not a good thing from a privacy perspective. This likely indicates that your data synthesis model is overfit, or there's some sort of leakage in your model. But it's actually very straightforward from a privacy perspective. So in the case where you have actually duplicated real individuals in your synthetic data set, where they have the same values in terms of quasi-identifiers or indirect identifiers, as well as sensitive variables, that's the easiest way of assessing risk, because that's a traditional re-identification risk. The next case that can happen is you can have individuals in your synthetic data set that look like real individuals on the basis of indirect identifiers or quasi-identifiers, but they may not have the exact same values as these real individuals when it comes to the sensitive variables. And so this is where it gets tricky. You need to have an altered way of assessing privacy risk for this situation. The last case that can happen with your synthetic observations is they could match nobody in the real world. And that's good from a privacy perspective. There's no risk in that situation. But again, it may indicate that your data synthesis model is not doing a very good job. So our main strategy for assessing privacy risks in synthetic data is an extension of traditional re-identification risk that we term attribution disclosure. So we have a lady in a blue cardigan here who we know is female and born in 1989. So in our synthetic data set, we can say, yes, I've found the lady in the blue cardigan. So the question now becomes, using the quasi-identifiers of age and gender, are we able to learn something new about this lady in the blue cardigan? And so that's where we start considering whether or not the sensitive variable, the NDC code, or the drug that she received is the same as what you would have seen in the real data set. So attribution disclosure extends traditional re-identification risk to say not just can I match between a real person and a synthetic record, but does that matching allow me to learn something new and meaningful about an individual in the real world? And so in particular, we do think it's really important to clarify that it has to be something new and meaningful. So in this table here, you can see the kind of different situations that can occur. So given that you've found the blue cardigan lady in your data set, the question is, first, is the value in the synthetic data set for the NDC code accurate? Is it similar to what you would see for the lady in the blue cardigan in the real data set. If it's not accurate, you're not going to learn anything meaningful about a real individual. So that has a low attribution disclosure risk. If the value in the synthetic data set is accurate, and it is highly similar to the NDC code for the real individual, the next question is that something meaningful? And so we make this distinction to try and separate out statistical inference that is quite common versus privacy risks with a strong negative implication. So if we were to look at the real data set and find that for some reason every single woman in the data set received a specific NDC code, us learning that from our synthetic data set is now no longer sensitive information, it's statistical inference that you could have gotten from population level data. So that's why we make this distinction. You have to learn something that's accurate about a real individual and something that's unexpected or something that you couldn't have otherwise gotten from aggregate population level data. And so this methodology is one of the ways that we assess privacy risks in synthetic data. And this methodology is something that we've published. The citation is on the screen. It's openly available for anyone to view. And based off of this methodology, we've assessed privacy risks in synthetic data sets, one of which is a hospital discharge data set and one of which is a COVID case data set. And so the average risk associated with these synthetic data sets was quite small. So you can see the largest value is, I guess, 0.0197. So if you were to compare that to a traditional re-identification risk threshold of 0.09, the risk in the synthetic data set is much lower than the acceptable threshold. The other key and popular privacy assessment metric for synthetic data is membership disclosure. So the difference between attribution disclosure and membership disclosure is that membership disclosure is looking at discerning membership in a data set without having to pinpoint which record in the data set belongs to a real person. So membership disclosure is asking, if I look at my synthetic data set, can I infer that a specific individual was used in the training data set to generate that synthesis model? And so membership disclosure is specific to synthetic data, and it's a very popular mathematical way of modeling overfitting and risk in synthetic data sets. So moving on to discuss data synthesis as a privacy-enhancing technology, hopefully we'll be able to tie things together and make some good connections with the other presentations today. So starting out with the promise, so the pros of synthetic data. So synthetic data is very dynamic, so you can apply it to a data set for a wide range of sizes. That's part of why at the beginning of this talk I showed you some different data synthesis strategies, because different data synthesis strategies can be applied depending on the size and the complexity of your data set. So if you have a huge insurance claims data set, you can use some really powerful deep learning models to synthesize those types of large data sets. Similarly, if you have a smaller clinical trial data set, you can use a more statistical machine learning model to still be able to synthesize it. So this is very, very powerful and dynamic and scalable as a technology. Another pro of working with data synthesis as a privacy-enhancing technology is that compared to anonymization, you don't actually have to go through and manually label the features in your data set to say, yes, you have a privacy risk, no, you don't have a privacy risk. There's no expert determination required to implement a data synthesis model. You kind of throw the whole data set at the synthesis model, and then you're able to generate a whole synthetic data set back. You don't need to have arguments with your colleagues about whether or not somebody's political affiliations would be a quasi-identifier. So that's a huge pro in terms of being able to do this at scale with live and large data sets. Data synthesis is also popular and powerful for working with small data sets. So maybe you have a rare disease or a particularly small clinical trial. Typically, to anonymize those types of data sets, you have to take your big black Sharpie to so many features that the analytic value of the data set may go down quite substantially. data synthesis does not require your black Sharpie to be used to the same degree. So it's very powerful. The other good thing is that data synthesis plays well with other pets. So, for example, certain data synthesis models can be trained using differential privacy. You can also train your synthesis model on data that has either been pseudonymized or anonymized already. After you've generated synthetic data, you can combine it with contractual controls or other ways of limiting access. So data synthesis is a flexible and dynamic technology that can be combined with other privacy-enhancing technologies to get the kinds of privacy guarantees you require, depending on your legal obligations for the data sets you're working with. And lastly, just to reiterate, since data synthesis is a machine learning-driven model, it's very automatable and scalable to work with new data sets. So very powerful in that regard. So those are kind of the main pros. What are the limitations? What are the concerns? What are the open questions? So working with synthetic data, the regulatory stance is uncertain. So that's why I had the disclaimer about being Canadian for the GDPR questions. It's a very emerging technology, so seeing where it fits in with privacy regulations is an open question that needs to be resolved over the next few years. And in particular, it really does require an accumulation of evidence to be able to show consistently that synthetic data is able to appropriately mitigate risks while retaining a high degree of data utility. Additionally, there's going to be some cases where you don't have any tolerance for discrepancies. So in those cases, you may be able to use synthetic data to conduct your analysis and validate your cohorts of interest or your outcomes, but you'll still want that real data set at the end to validate your results. So in that case, it can require a little bit of additional infrastructure to facilitate that kind of validation of analysis. Another concern is that if you've got a giant complex data set, you're going to need a giant complex model to synthesize the data set. So it can be quite computationally intensive. There's fantastic opportunities for parallelization and utilization of GPUs to try and make things run more efficiently, but it can be quite computationally demanding, especially when you have large data sets. And lastly, this is a question that affects the privacy industry in general, but how can you report privacy risks appropriately? So the methods that I described are privacy assessments that are reporting the average risk across your data set, but there's always a concern about how outliers are handled, as well as the privacy risks associated with outliers. So that's kind of an industry-wide concern with how to work with these data sets and how to report risk, but it's definitely present with synthetic data. And you kind of have that additional question because you need to not just be able to assess risk appropriately, but potentially understand how well your data synthesis model is able to reproduce outliers or model them appropriately. So those are some of the main kind of open questions when it comes to synthetic data. Overall, though, I think synthetic data is a very powerful emerging privacy-enhancing technology and has a lot of opportunity in the healthcare space as well as other fields. So thank you very much for listening.
Thank you very much, Lucy. Maybe also the same question to you. We heard epsilon budget as the trade-off between privacy and utility. Here you talk about under and overfitting. What are the questions to start the conversation as DPOs with data scientists? What would your advice be?
That's a great question. I think that some of the main priorities would be ensuring that you're actually assessing this stuff empirically. Having the information available to make decisions is so critical. So being able to work together between regulatory users, data scientists, to be able to come up with what the metrics of interest should be for your use case. So in the case of data utility, if you know how your data is planned to be used, go ahead and calculate those workload or narrow utility assessments so that you can make an informed decision. Same goes for privacy. I recommend calculating it every time you work with a new data set just to get that confidence that you're consistently getting good results and to continue that accumulation of evidence. So once you have those metrics in hand, that's when you can start having the prioritization. It can be very helpful to have thresholds. So for example, with de-identification, An often used threshold of acceptable risk is 0.09. Having that can really facilitate decision making and ensuring that you're below the privacy risk threshold for acceptable use. And you can set up similar utility thresholds as well to aid in decision making.
Another question before I open the floor is, what we see that in data sets, sometimes behavioral patterns may still exist. To what extent does differential privacy provide a measure to such attacks that are based on re-identification, based on behavioral patterns?
Yeah, so with longitudinal or behavioral data sets where you have multiple observations over time, data synthesis can still be a powerful privacy-enhancing technology. It just means that as you assess your utility and your privacy implications, you may want to adjust the way that you calculate those metrics so that you're able to take into account the behavioral or temporal patterns. And yeah, differential privacy plays very nicely with synthetic data. You can use differential privacy as you train your synthetic models, synthetic data generation models. It's a very good way of adding that extra layer of privacy mitigation, privacy risk mitigation.
So to take home, I think it's important to address the quantification of risks with your data scientists. You see that we did not touch on that so much with homomorphic encryption. We talked about differential privacy and synthetic data a little bit more on the quantification, but the metrics, like the reports that you will be receiving and what they mean, that could be a good tool to implement and facilitate this discussion with the data scientists. I'm going to walk to the back of the room for the first question of the audience. 1 second, please.
Thank you. Marco Melia from Polytechnic Torino. So actually this builds on the last part of your presentation. I'm kind of puzzled here. How can we consider synthetic data privacy enhancing tool? Because I mean, if I think about homomorphic encryption, I have an hard guarantee that I want you to compute 2 plus 2. I tell you 7 and 19. You do the plus, you tell me minus 12, and I can decode it and get it 4. That's a mathematical proof. It works. Drawback, it takes 1,000 seconds. With differential privacy, I tell you 2.1, 1.95, you do the math, and you tell me 3.95, and I know the error. We have been debating with the epsilon, which is the right epsilon here and there. Here, what kind of guarantee can you give me that my face is not going to be generated by the gun? Or what kind of guarantee can you give me that my face will not be included in the generation or the training of the GAN or the variation autoencoder? So what kind of guarantee? Here I don't see any sort of hard, neither soft guarantee, just a practitioner idea that if I generate random data, this is going to kind of protect the privacy. But if I look at some guarantee, I don't see really nothing here, right? Am I missing something or what?
No, that's a very valid concern. And so part of why you don't see it empirically here is because this is a non-technical presentation. So for each of the different data synthesis strategies, so sequential synthesis, variational autoencoders, and GANs, there's different built-in mathematical characteristics to how the models are fit to prevent overfitting that would lead to that kind of reproduction or duplication of exact values. So for example, with sequential synthesis, we often use decision trees as the different models to use in sequence. And there's a very easy to visualize restriction to prevent overfitting. We ensure that as you build your tree, which has all your splits and different decisions, that the terminal nodes where the predictions actually lie, we ensure that there's always at least 5 or 10 observations in those bins. So as we build the models, there are built-in restrictions to prevent overfitting. I'm sorry I didn't get the chance to get into that, but that's a completely valid concern. And depending on the synthesis model you use, it's going to be guaranteed in different ways. Additionally, you can always use differentially private gradient descent as part of your training to get that extra additional mathematical guarantee. But there already is some degree of security built into the synthesis models, depending on the strategy you use.
Okay, thanks.
Hi, this is Isabel Orbera. Thanks for your presentation. I was wondering, when you need to get value from your data, how would you argue that synthetic data is better compared to other anonymization techniques? Thank you.
How we argue that it's what, sorry, compared to anonymization?
Yeah, to get value from your data. So compared to other anonymization techniques, I would like to hear your arguments about why.
Yeah, I think some of the main benefits are the fact that you can generate your synthetic data without having to go through and pick out which variables have privacy risks versus which variables don't have privacy risks. Oftentimes with other anonymization techniques, that kind of debate is a bit of an art and a science, and so there isn't necessarily an empirical correct answer for which variables should be considered to have a privacy risk versus not a privacy risk. And so the nice thing with synthetic data generation is you don't have to have that argument. The data synthesis model is going to be comprehensive and it's going to touch on all variables in your data set, so you don't have to prospectively define here's a privacy risk and here's not a privacy risk. So that's one of the main advantages that I see. Other advantages include the scalability, so working with very large to very small data sets in a dynamic way, and the fact that it can be automatable.
But would you measure value in terms of privacy only, or do you have any other measures about that? Or is it use case based, probably? Or?
Yeah, I think that it's also valuable in terms of time to turnaround, so being able to facilitate data access quicker. So because you don't have to go through and have those arguments, discussions between different experts and different people who have different subject area knowledge, you can implement data synthesis faster and hopefully get access to data faster.
Yeah, I guess I had a question. I'm not sure how much I'll be able to formulate it quickly, but at an abstract level, it's like how multidimensional is the privacy utility trade-off that you measure there between what definition of privacy and what definition of utility? I may have a misunderstanding about synthetic data, but I've understood like synthetic data is often generated with a particular utility in mind, with a particular thing that you're aiming to get at. And if you maybe need a different utility, you generate a different data set. But for privacy aspect, like especially if you move beyond like the Canadian one where you gave the identity disclosure, how do you deal with like the linkability one? I mean, this kind of ties to the previous question as well. Like maybe it wasn't the intent of the data set to be about the likelihood of someone's face being there, but rather just had some other aspect of face that was the utility variable. And as a side effect, well, faces are actually still kind of recognizable, but it wasn't something that was measured as like you can't identify this person as having come from there, but it's still a feature that you could recognize from that face. And so how do you deal with those side aspects of not it being an identity aspect, but just semantic stuff that you can get? I mean, previous pseudonymization techniques deal with that split as well, right? K-anonymity still could have had sensitive values all relate to that K, so you had Li diversity that came in. So I guess it also comes to a question of like, are there guidelines of when you should get another pet involved when this is maybe not, synthetic data isn't solving enough of the privacy issues?
Thank you. That was a very comprehensive question. I feel like you may have started to answer some of it yourself, but here would be my take on it. So I think that when it comes to both utility and privacy assessments, it's important to not get too bogged down in your narrow utility assessments. So you do also want to be conducting these broad utility assessments that look at the patterns and relationships in your data set at a kind of structural and analysis agnostic manner. And so the ideal broad utility or privacy metrics are actually going to be predictive of narrow or utility specific, analysis specific utility assessments. So having that mix of broad versus analysis specific can be a really good way to guarantee the generalizability of your findings. And we actually have a recent publication assessing the relationship between broad and narrow utility assessments that shows that they can be predictive of one another. So having a kind of dynamic approach to how you assess utility and privacy can be really beneficial in terms of getting comprehensive and generalizable results.
I want to be mindful of time as well, so I'm going to thank you for all the speakers.
Can I ask just one more question? Very quick.
If it's quick, yes,
yes.
please, then we wrap up.
You mentioned threshold, the privacy risk threshold, 0.09. Where can I find that number? And is there like a reference that are actually used for different types of utilization of the databases?
Yeah, so that number comes from different regulatory bodies. So I believe that is the value that has been used for Canadian and UK regulatory bodies, but I can find you after and send you the exact citation.
Thank you so much.
Thank you all very much.